Hello everybody, Root Beer here. Thank you for joining me as we finish off the 2011 Hypatia contest. So we've got question number 4 here. Let f of n represent the number of ways that a positive integer n can be written as the sum of positive odd integers. For example, f of 5 equals 3, since these are the only ways we can write out 5 as a sum of odd integers. 5 ones, 2 ones and a 3, and then just a 5. F of 6 is equal to 4, since 6 can be 6 ones, or 3 ones and a 3, 2 3s, or a 1 and a 5. Okay. So this is what we're going with, and it puts me in mind of a more well-known mathematical problem called the partition problem, which isn't odd integers, but it asks, in how many ways can I write a natural number as a sum of other positive integers? And as I recall, there isn't a very satisfying answer to this, so maybe they've chosen odd numbers so that things work out a little nicer, or maybe they're not going to ask us to completely characterize f of n. But, if you've seen the partition problem, this is the sort of thing that jogs your memory. And if you like this problem, you tried it, if you like it, or if you like it after seeing me present it a bit, certainly go and look up the partition problem. It's very interesting. I believe it does have a solution if it's not. I think it's a recursive definition, but I don't know enough, so that's all I'm going to say there. Okay, so what are we asked to do? So find f of 8 and list all the ways 8 can be written as a sum of positive odd integers. Okay, so that's I was talking a bit about this when we did question 3. This is sort of dipping our toe in the water. We've got a brand new function. Do they understand it? Can they just compute something as simple as f8? Okay, so whether or not that's going to be hard, I don't know. It shouldn't be. It's a part. What would b part be? Show that the function's always increasing. So f of n plus 1 is always greater than f of n for all n greater than 3. So I'm guessing maybe that breaks down for 1, 2, and 3. I mean, clearly it's true for f of 5 and f of 6. And if that's the case, that should tell us that f of 8 is, so f of 7 would have to be at least 5, f of 8 is going to have to be at least 6, so that helps us a bit. And then C part, proof that f of 2n is greater than 2f of n for all integers n greater than 3. So I'm wondering if it's got to be greater than 3, because 3 is the the smallest odd integer other than 1. I don't know, but I'm thinking that's probably it. Okay, Well, in the absence of, I know that I want to show I'm guessing to prove B, we'll probably really have to take a look at the examples F5 and F6 that they gave us. Because there's only one more with F6, so which one's the odd man out? For F8, I think we just sort of have to list them out. So let's see what we can do. So 8's going to have to be, I think the easiest way to do it, start with 8 ones, because that's certainly how they seem to be listing theirs. Start with it all in ones, and then take away 3 of the ones, put a 3. Take away 3 of the ones, put a 3. Take away 3 of the ones, put a 3. Let's see where we can go from there. So let's take away 3 of the ones. So we'll just have 5 ones left. And put a 3. And I've got some ones left over, so we can do that again. And that's about it. Now I can do the same thing, take away some ones and put a 5. Okay. And so I can't take away any more 5s, but I do notice I can take away 3 ones and put a 3. So 2, 4, 5, there's got to be at least another one. So we did the 3s, 5s, could not really go anywhere with the 5s. The last thing to do, I guess, is 7. That seems like a little too low. Seems like I'm missing one. All ones. So this is where having a strategy for listing them out in a particular order is helpful. So what I've got going on, start with all 1s. Then the next odd number up is 3. See how far I can get with just only 3s. Okay, so we got 1 3, 2 3s, can't get a third 3 in there. Then we can move up from 3, put in a 5 and say, okay, 5 and a bunch of 1s. And then we'll take those 1s, turn them into 3s as much as we can. Then when that runs out, we'll add in another 5 and then ask, 3s that we can do. And then once we've exhausted all the possible 5s, move up to 7, 7, then add in all the 3s that we can. Then move up to 7 and a 5, add in all the 3s that we can. 7 and a 5 and a 5, add in all. So that would be my general strategy, and that would really get tedious for larger numbers, but I'm not seeing a hole in that, so I think these 6 that I've got is it. I think f of 8 is going to be 6. Now, in terms of justifying that, I think if you explained what I just did and said this is my pattern, I mean, you can note things like at most 1 7, at most 1 5, at most 2 3s. And I think if you were to make some observations like that, you could also clarify it. But I imagine you get the marks for, it's probably worth 2 marks is getting f of 8 equals 6, maybe with some justification, and then actually writing out the list would be another mark, probably. Or maybe it's 3 marks, so 1 for the final answer, and a mark for each set of 3 of these. I don't know. I wasn't there when they marked this one, so I don't quite know what the breakdown was for this. But we've got 8, and it's really written in all the ways that I think we can. Okay. So f of 8 is 6, and now we're being asked to prove that f of n plus 1 is greater than f of n. This would sort of force f of 7 to be 5, by the way. So if I wanted to, I could double check this by asking, how many ways can I write 7 really quickly? So 7, I could have 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. I could have 1 5. I could have 2 3s, and I could have just 1 3. And I can't think of another one in there, so yeah, I'm a little more confident that my 8 equals 6 is better, because this doesn't seem to be growing very fast. Alright, now, in terms of answering B part, so I'm going to throw my 5 up here. So 5 was 1 plus 1 plus 1 plus 1 plus 1, 1 plus 1 plus 3, just because I want to be able to compare things. And I'll throw out my 7 one as well, but I'll properly order it. But writing all those ones is a little tiresome. One plus 1 plus 5. Now with odd numbers, it's very clear to see that I think that we're going to get another one. Because with odd numbers, there's always the 7 equals 7, 5 equals 5. One more. And 3 plus 3. And then 5 plus, well, 1 plus 5, I think is how they wrote it. Now, I need to be able to increase by 1 each time. And as I say, the odd numbers, they catch my eye because they got this unique 5 equals 5, 7 equals 7, 9 equals 9 sort of thing. Even numbers don't quite have that. But if we take a look at the bottom ones here, so 5, 5 plus 1, 7, 7 plus 1. I'm thinking that the way we go up is that I can always add 1 to each of these, and it gets me something in the higher one. Now with odd ones, we also get for free something that we wouldn't have had, something that doesn't have a plus 1. And so that tells me that it's true for odds. But with evens, how does it, what's the new one? Well, for evens, we can always, this 5 plus 3 and this 3 plus 3, they're the ones who are standing out for me now. So how do I express that? So for 2n, so we can always add 1 to everything that we've had before, but now we're looking for expressions that are guaranteed to exist that don't have a 1 in them. For odds, it's quite clear that we get, 2n plus 1 equals 2n plus 1. But for evens, I think if you go n plus n, if n is odd, or n plus 1 plus n minus 1, if n is even, and this would hold true, so n's got to be greater than 3, so then this guy here would definitely be greater than or equal to 3, because that would be at most n minus 1, which is at least 4 minus 1, which is 3. So I think that's it. I think we got it there. Okay. So now the question is, how do I write this up? Okay. So what do we do? I'm having trouble thinking of how to start this. So any expression for n as a sum of odd numbers can turn into an expression for n plus 1 by simply adding a plus 1 to the end, i.e. 5 equals 5, 6 equals 5 plus 1. 7 equals 1 plus 1 plus 5, 8 equals 1 plus 1 plus 1 plus 5. So you have to say to the end, but it's adding an extra 1 plus 1. So this tells us that f of n plus 1 is at least as big as fn. And I'm saying to show f of n plus 1 greater than fn, we only need to find an expression for n plus 1 that has no plus 1s in it. Let's not say plus 1s, let's just say 1s. Since that means it doesn't correspond to an expression for n. Okay? You could probably argue that there's some back and forth, that every expression for 6 that has a plus 1 in it corresponds uniquely to an expression for 5. And you can do some back and forth there. And if you wanted to, you could say something like bijections. But I think the main message is clear. Adding 1 gets us something for n plus 1. So we can at least just sort of copy each expression over. And so that shows that f of n plus 1 has to be at least f of n, because I can have as many expressions in the list. Just add 1 to all the ones in the list for fn. So now, if n plus 1 is odd, then since n has to be greater than 3, what have we got here? So n has to be greater than 3, so it's at least 5. Then since n is greater than 3, n plus 1 is greater than, well, it's greater than or equal to 5. Yeah. So n plus 1 equals n plus 1. I'd probably write it like this so they're not confused with a plus 1 here. Is an expression with no 1s. Okay. And if n plus 1 is even, then since n is greater than 3, n has to be greater than or equal to 4, therefore n is greater than or equal to 5, but because it's even, we know n's got to be greater than or equal to 6. Let n plus 1. Okay, so let n plus 1 equal 2k. Then if k is odd, n plus 1 equals k plus k will do. So we'll have no 1s. If k is even, then k has to be at least 4, because k is greater than or equal to 3. So if k is even, k has got to be greater than or equal to 4. So k minus 1 is greater than or equal to 3. Therefore, n plus 1 equal to k plus 1 plus k minus 1 has no 1s, and that does it. So we have found an extra thing that we can add to our list. Quite easy with n plus 1 being odd, a little more work if n plus 1 is even, but we have found something that has no 1s. Okay, so not bad at all. And then now for a C part. Prove that f2n is greater than 2fn. Okay. So we can't just do the plus 1 trick, because that would only have fn, but what could we do? I think So I was going to say, can't we just use, like, if we got 5 is equal to this expression, and this expression, and this expression, then couldn't we get 10 being equal to this plus this, and this plus this, and this plus this, and this plus this, and this plus this. These are the squiggly ones, by the way. And this plus this. Or is there going to be some sort of overlap here? Am I going to be double counting? Because that here certainly gives me 6. And I think if I had 4 expressions, it would give me... So there's 3 with this one, 2 with this one, 1 with this one. I think it would give me 4 with the other one. So... Squiggles with itself, and with 1, 1, 1, 1, 1, 1. So that'd be 4 of those, 3 of those, 2 of those, 1 of those. So I think it would be if f of n equals k, then we'd be able to show f of 2n was at least equal to k times k plus 1 over 2. And that's bigger than 2k, maybe? So that would have to be, so k plus 1 would have to be bigger than 4k. And where would we get to? So then that would mean k plus 1 has to be bigger than 4, but k has to be bigger than or equal to 3. And I think that's okay because... no, I think there's a little bit more missing here. Thing is, what would be... So we need... So n's greater than 3. So the smallest one would be n being equal to 4. Well, I don't have... I never listed out 4. I did 8. So I'm going to copy 8 and I'm going to create 4 and see, is there a way that I can make these? So right now we're just sort of playing around to see what the answer might be. So 4 could be 1 plus 1 plus 1 plus 1, or it could be 3 plus 1. 8 is 1 plus 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 1. I mean, there's an abundance of stuff here that we don't have with the 4s. And then 3 plus... Oh, no, it's 1 plus 1 plus 1 plus 5. Three plus 5, and then 1 plus 7. But notice that my idea is coming through. If we have the blue one, or purple one, I guess, we have purple and purple. And we have purple and orange for this one. And if I just quickly rewrite these ones, I will get orange and orange. So that gets me 3 of them, but that's, I mean, we would need 1 more to get 4. We'd need 2 more to be bigger than 4. And we can get 2 more of them. Can this always be done? So I'd say the key thing here is 4, or n is limited. Expressions at most contain an n. Okay. But expressions for 2n, there's a whole mess of odd numbers after this that between n and 2n. And so, for example, with the 4 here and the 8 here, you'll never get a 5 in any expression for 4, but we can do 5 plus 3, and 5 plus 1 plus 1 plus 1, and 7 plus 1. These are things that we couldn't have had before. The question is, can I take this all and turn it into the result that they want? So I say it's quite clear that pairing up things for 4 give us some expressions for 8. And I think that gets us most of the way there. As I say, I think that gets us k times k plus 1 over 2. And, that... for for k values, so we need to be bigger than or equal to 2k. So this isn't quite there yet. For k plus 1 greater than or equal to, what would I need? So it'd need to be 5 or more. This is true. Actually, for 5 or more, this specifically is true. I will make it 6. Okay. Now, k plus 1 being equal to 6, I think that's 8, which we've already worked. So as long as I can show... So k plus 1 being equal to 5. So as long as we do something beyond 7, we're good. We just need to show a couple exceptional cases, maybe? The real question is, does this adding things in pairs work? Or have I made some sort of a mistake? That's the real challenge. Are my hunches correct? It's clear when we do the 8s, but if... what if something falls apart when we do the 10s or something? Well, let's see if we can show this. So, suppose A1, A2, up to some number, I don't know, let's say n is already in use, so let's say AX is equal to n, and B1 plus B2 plus BY is equal to n. Not necessarily different expressions. Because this way I can then double up on the 1 plus 1 plus 1 plus 1 stuff. So then it's clear that 2n is equal to A1 plus A2 plus yada 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 plus B1 plus B2 yada 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 plus BY. But is this the only way to express it as such? And I'm thinking no. So let me see if I can just sort of talk out how I'm thinking about this. So I think we would get a unique expression for the very small cases that I've got working on here. So like I used 4, and yeah, I could highlight and say, yes, this works. But I think as soon as embedded in the A1, A2, A3, and so forth, as soon as there are 2 expressions that both equal, say, 5, so there's a couple ways. So as soon as I were to do n equals 6, for example, inside the n equals 6, there are a couple expressions for 5. And could I not sort of interchange those, is what I'm thinking. That's the thought process here. Is could I not sort of interchange those? I'll show you what I mean. I'm going to go on a hunt to see if I can find one of these. Oops, wrong button. But yeah, as soon as I have something like 1 plus 1 plus 1 plus 3, and then 1 plus 1 plus 1 plus 3. These are both expressions for 6, and therefore expressions for 12, but this is not the only way to do 12. We could do 1 plus 1 plus 1 plus 1, and then plus the 3 plus the 3. And those are also two different expressions that could have been added together. So I'm thinking this whole plan here won't work. So I'm going to have to go back to the drawing board. What can we do? I want sort of, if I'm going to do it like B part, I want to sort of be able to take 2 copies of Fn, duplicate them, and then add in a couple extras for F2n, considering how big it is. Do I need to use the result I proved with B? Because that wouldn't really help. That would just show me that f of 2n is at least as big as fn plus n. Not going to help me. Well, suppose I were to do something like 1 plus 1 plus yada 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 plus 1 is equal to n, and then any other expression for n, including that one, I can combine those, I think, in a unique way to get 2n. Okay, and then maybe the blank plus 1 equals n. Maybe one of the two that I was talking about just a moment ago would help us. So that would then, if I can combine them this way, then I could show that f of 2n was at least as big as fn. But of course we already sort of know that from B part, that the function f is increasing. Where to go from here? So how do we go from 4 to 8, if that is even the way we should be thinking about this? Yes, I was lucky enough that I could just sort of duplicate these, but the second I get too many 1s, i.e. with 6, this goes down the drain. I need a way to take the ones with 4, and so there's 2 of them with 4, I need to get 4 of them in 8, and then have some extras. But I don't have 4 of them in 8 that only sort of use parts from 4, using 1s and 3s. So that's no good. I'm betting it'll probably have to be an odd-even sort of thing. Now, I mentioned before different... So any expression that uses... So any expression for 2n that uses an odd number k with k greater than n must not have come from my sums involving n. Right? Here's my current thought. Here's my current thought. If n is odd, let a1 plus a2 plus, up to some ax equal n. Then we can write 2n is a whole bunch of ones, n ones, plus this expression. We can also write 2n as just n, because n is odd, plus this expression. Okay. So I think this gives us 2 times f of n ways to write this. Minus 1, because we'll be counting the 1 plus 1 plus 1 plus n case twice. Once when it comes down in the second one, and once when we just have the n up here. But other than that, I think we can say so I think this gives 2fn minus 1 expressions. Now I need to prove that. I need to justify that in some meaningful way. But this is my current thought. So we're just going to go with it. So with n is odd, I imagine with n is even, we could do something similar, like put the plus 1 here. And then, so that would get me 2 fn minus 1 expressions. Maybe with the even case it's minus 2 or something like that. But then, n greater than or equal to 3. So 2n so n is at least 4, so 2n is at least 8. So 2n is so 2n minus 1, 2n minus 1, and 2n minus 3 are odds that are greater than n. So if I did the 2n minus 1 plus 1, that's an expression, and 2n minus 3 plus 3, that's an expression, or 2n minus 3 plus 1 plus 1 plus 1, and that's an expression. So that would get me 3 expressions. So I could even do the minus 2 here. So I think that's it. So we get these 3 expressions here for free, and I think we can do 2fn minus 1 or minus 2 or something expressions there. Okay. That seems like a workable plan. Now, I thought I had a workable plan before with sort of those triangular numbers. That didn't quite work, but I think this one will, because I think I can quite quickly tell apart 2 expressions coming from my first thing where I created an expression using n ones. And then the one expression using an n. I don't think there's any problems like the one I had with the interchanges before. So let's see if we can write it up. But this is the general strategy, and I would at least write this down quickly if I thought I was running out of time. Okay, so we'll do this by cases. Let n be odd. And consider an expression. I'm not going to bother to say an expression using only odd numbers. These are the expressions in the question. Okay, so an expression like this. then we can create two new expressions for 2n, i.e. 2n is equal to n plus a1 plus ax. 2n is equal to all these 1s plus a1 all the way up to ax. Okay, so we can create two new expressions unless the a1 is equal to, unless they're all equal to 1, or a1 is equal to n. Okay, so this is my claim. In this case, for these a1s up to ax's, so what's our conclusion? This would make fn minus 2 expressions, because we're excluding these two, times 2, so that'd be 2fn minus 4. And then I can get the 1s and the 1s, the n and the n, and then the 1s and the n, and that'll get me 3 more. Okay. Suppose for two expressions, a1 ax and b1 by, that they make the same expression. Okay, that's the idea. So we claim that we create two new expressions. I need to actually show that the n plus the ax, the a1 up to ax's, and the 1 plus 1 plus 1 plus the a1 up to ax's, that these really are unique. They have to come from a1 up to ax. They can't come from another sequence b1 up to b1. So we're going to show that if these expressions are the same, then the b1s and so forth are the same. If n is in either expression for 2n that we get, so then since a1 plus ax and b1 plus by are not the n equals n expression, because remember, I didn't allow that one. Then we have n is equal to n plus 2n is equal to n plus ax, n plus b1 plus by, and therefore they are the exact same expression. So here when I'm using the equals, it's not that they're both equal to 2, it's that they are the same exact expression. The question is, can I rearrange some of the numbers? That's the problem, is can I rearrange some of the numbers? And I think there's probably a more elegant way to write it. So since I couldn't have the n equals n expression, then all b1 and by's have to be less than n, all the a1s up to ax's have to be less than n, and that might be something to add in, but the point is, if these two are the same expression for 2n, then just getting rid of the n's, which are clearly not part of the a1 up to ax's, we must get the same expression. if no n in either expression, so our AIs and our BJs have to be less than n. So if there's no n in either expression, if there was an n in one expression, there'd have to be an n in the other, and then we'd be able to reduce it down. So then both expressions have n ones, and so we get 1 plus 1 all the way up to these guys. And then 1 plus 1. This is the same expression for 2n, and therefore these guys are the same expression. Okay, now I admit my writing there, very inelegant. I probably wouldn't give myself good marks for that because I'm not really expressing everything. This question's been going on long, so I'm trying to be a little less rigorous and get moving. But I would say the key details are there. So we've got the key thing that we're trying to prove. Say we have two expressions that when we do one of these two, we get the same expression for 2n. Well, either there's an n in one of the expressions, and therefore, since it's the same expression for the two n's, there's an n in the other expression. But since I banned the n equals n expression being one of the a1 up to ax's, both of these sums have to use only odd numbers that are less than n. Okay? And then, so that forces them to have the same expression. And the same thing with the ones. Because there's no n in here, then they both have to be this sort of expression, and that means that they both are the same expression, because you just remove n ones. Okay. So we have 2fn minus 4 expressions. And we can also get 2n is equal to n plus n. 2n is equal to a whole mess of 1s, because remember we didn't allow that to be the a1 plus ax's, so just 2n of those. And finally this one right here. Okay, so therefore we have 2fn minus 1. So we just added 3 expressions for 2n. Alright, so that's fine. If n was even, then only one expression for n uses n minus 1, i.e. n is n minus 1, because that one's got to be odd plus 1. So the same, and I'm writing the same because I think if somebody gets what I did here with the sequences, then they'll understand it works the same way with the evens, just using a different fixed sequence. So the same reasoning, take an a1 up to ax equals n. That is not the 1 plus or the 1 plus n minus 1 equals n expressions. We get 2n equals expressions. And again, same sort of reasoning will show that this is a unique process. There's probably some fancy, quick way to do it here, but since the idea here is that if you have an n in the expression here, there's only one expression, n equals n, for this odd n. So since we're disallowing that, both of the A sequences and B sequences can't have any n's in them. If an n appears anywhere in the expression, it's got to be the n plus the sequence way of writing it. So that both have to be the n plus the sequence way of writing it. And so that tells us it's got to be the same expression. Or if there's no n at all anywhere, then we just have to have the ones and the ones, and that gives us the same expression. Well, the same sort of reasoning can work here. Only one expression uses n minus 1. So if there are any n minus 1s in the a1 up to ax expression, the expression for 2n that we get, it'll have to look like this. The b1 will have to look like this as well, and that'll force the b1s, the b sequence to be equal to the a sequence. And if not, then we just have the plus 1s, and everything goes on from there. I'm not explaining this one well, but it's been a long day. Anyway, you can sort of get the idea here. I imagine, considering how long this is, I have a history when it's not the Euclid, when it's the Hypatia and the Galois, of doing a detailed expression, and then I go and look up their solutions online for whatever reason. And they always, take things quite quickly for granted that I have spent quite a long time in these videos actually doing. So I'm just going to sort of cut my losses. I'm saying this works, and I'm moving on. So we once again get 2 fn minus 4 expressions. And then we get 3 more, plus 3 more for the n minus 1 plus 1 plus n minus 1 plus 1, the n minus 1 plus 1 plus 1s, and all the 1s. So, no matter the parity of fn, or no matter whether or not n is even or odd, we get 2 fn minus 1 different sequences. Hooray! And finally, since n is greater than 3, we notice 2n minus 1 and 2n minus 3 are distinct odds, with 2n minus 3 being bigger than n, because if it were equal to n, it's certainly not going to be less than n, but if it were equal to n, we'd have 2n less than n plus 3, and that's true because we got n plus n, and n is more than 3. So we get 3 new expressions. 2n is 2n minus 1 plus 1. 2n minus 3. I don't need 3 expressions. I'm just writing them out because they're the only ones that I can get with these ones. So we have 2fn minus 1 plus 3 is at least what f of 2n is. Therefore, f of 2n is at least 2f of n. Well, it's more than 2f of n, because this expression here is 2f of n plus 2. And we only needed 2f of n plus 1. So we got what we want in the end. It actually fell out pretty quickly after that, so maybe I could have spent a bit more time with this sort of unique expression stuff, but it's a pain in the neck to write, and I think as long as you have the main beats there, you'll get the marks. And there it is. So we have indeed shown that it's bigger than 2fn. And more than that, we've got 2fn plus 2. And for 4 we had 2 expressions, and then we had 2f of 4 plus 2. We got exactly 6, which is in fact f of 8. So that's nifty that it works out that way. Okay. So there we go. So we needed to have some extra odds that were in no way going to come from any smaller expressions, and we had to really figure out how do we get some new expressions from the ones that we know exist for Fn. Okay? That was the main idea behind C. But it has been a long Hypatia. At least this question feels quite long. So I am ready to take a break. It was a good Hypatia. I liked it overall. I especially liked question 3. It was a lot simpler, I thought, than most question 3s. But I like the 2011. I can't wait to see what's in store for the 2012 Hypatia, which will be the next Hypatia I do. However, in terms of my hierarchy of contests, I think the next Waterloo contest I'm doing is the 2011 Euclid. So if you want to join me for that one, it's great practice even if your next contest is a Hypatia, because the Euclid does more writing and practicing writing things up there. Okay, but that's question 4, and you guys have been wonderful. Feel free to like or subscribe or any of that stuff, but I will see you for more contests in future videos.